We're going to do a few problems on simple resistor networks, actually adding in some numbers for resistors. In particular, we'll be looking at the cases I just talked about in the previous video. First of all, the unloaded voltage divider, and second, the loaded voltage divider. So a voltage divider, again, is two resistors in series. One example of voltage dividers are potentiometers. We'll label R1 as being the top resistor, R2 being the bottom one. And a problem, which we're going to end up caring about quite a bit, is to start with one voltage difference, say 0 volts and plus 12 volts DC, such as what's put out by our Eurorack power supply modules, and then design some resistors, a network of resistors that turns this plus 12 volts into a positive 1 volt DC. And then I'm putting an additional constraint on the problem, which is to make sure that this resistor network that performs this transformation of 12 volts to 1 volt draws about 1 milliamp of current. Now this circuit does have a very specific purpose. Not only is it a great example problem and something we'll see many times, and among other things, it resembles a potentiometer, but also we need to build this particular circuit next week in order to tune our VCO, our voltage controlled oscillator, to have a proper tuning response. So as you've been reading about, VCOs typically have a standard of 1 octave of pitch change for every 1 volt of input. So for instance, if we tuned 220 hertz to 0 volts, we would want 1 volt to be 1 octave higher, or 440 hertz, 2 volts to be 880 hertz, and so forth, as we moved from 1 octave below middle A to 1 octave above middle A. And we'd want to keep that regardless of temperature and other changes in our system. Right? So this is actually the beginning of a tuning circuit, which we're going to need next week. So we do this. We start with the now hopefully familiar voltage divider equation, which is that the output voltage is going to be this ratio, which is the bottom resistor divided by the sum of the two resistors times the voltage in. And then we insert the values for our particular problem. Now, I didn't have R1 and R2 labeled. I had R1 and R2 labeled, but I also had particular voltages, so 12 volts on the output and 1 volt on the input. And then we use Ohm's law to decide what current it is we want to produce. So R1 plus R2 needs to be 12 volts over 1 milliamp, which is to say the total resistance needs to be about 12 kilo ohms if we're to have 1 milliampere of current. Combining these two equations lets us solve for one of the resistors, say R2. So R2 would be the ratio of the voltage in to out times that total resistance of the circuit, or 1 kilo ohm for the bottom resistor R2. That allows us to get R1, since R1 plus R2 has to equal 12 volts. That means that R1, the top resistor, needs to be 11 kilo ohms. So the top resistor should be 11 kilo ohms and the bottom should be 1 kilo ohms. And as I've shown here, now with labels on it, this configuration of resistors would give us 1 volt output from 12 volts in. This configuration looks fairly reasonable because it draws a milliamp, and the smaller resistor is on the bottom of the circuit, meaning most of the voltage drop is already done with through the 11 kilo ohm resistor before we get to the 1K resistor. Now, if you wanted to still have 1 volt, but have a different amount of current flowing through this circuit, you could simply multiply each resistor by a certain number. So for instance, a 22 kilo ohm and 2 kilo ohm resistor in those positions would still give 1 volt out. However, the amount of current drawn would be half as much as in the shown example. Now practically, it's very hard to do this using common resistors. So if I look at my resistor drawer, they tend to increase by 20% for each resistor. So I have 1K resistors, no problem, 1.2K resistors, 10K resistors, 12K resistors, but most sets actually won't have an 11K. So if you can't find 11K resistor, you're in trouble. You could, of course, use a 10 and a 1K together to make one in series, but you still have a little bit of a problem, which is the accuracy of those resistors, which is typically 5% these days, maybe even as bad as 10%. So even if you went and you chose a bunch of resistors from the drawer, you really wouldn't be able to get exactly 1.00 volts output because you simply don't have resistors that are that accurate. So in fact, what's often done is to use a potentiometer anyway, but it would be rotated such that that was about 11 kilo ohms on one arm and one on the other. Of course, 12K pots don't exist either, so you're likely to have to do this in a different range, say the 1K range or 10K range, perhaps. Now I want to consider a more complex configuration, which is the loaded voltage divider. So it will divide voltage from 12 volts to 1 volt, but what happens if we actually try to use that voltage? So in this case, we take a load resistor. That load resistor is shown over here, now attached across the output terminals. And what we will find is that in general, the loaded voltage at the terminal is not the same as the output or unloaded voltage, which before we found was 1 volt for this configuration. So I'd like to determine how much it changes, and then think about maybe how to compensate for it. This is, again, a realistic problem because we want to make, say, 0 and 1 volts to tune our VCO. And the input resistor on our very first VCO is going to be about 100,000 ohms or 100 kilo ohms. So I've drawn that in here as a 100 kilo ohm resistor on our, again, our load. Loading that circuit or putting a resistor on is always an effect of changing the output voltage. So to figure this out, we have to think about those two bottom resistors. And we recall from the last quarter that there is a reciprocal rule, shown as equation 6 here, which tells us how to take two resistors, which are splitting an incoming current into two parts and then recombining them afterwards. So two resistors, R1 with current I1 and R2 with current I2 in parallel, connected to the same voltage difference. And take these elements and combine them into one equivalent resistor, one equivalent resistance with a total combined current of I1 or plus I2. And that equivalent resistance is given by this reciprocal law. 1 over our equivalent is 1 over R1 plus 1 over R2. And here in equation 6, it's very easy to remember the law this way, but not always so simple to implement the mathematics with all these inverses. And so you should take a few minutes and convince yourself that equation 6 is absolutely identical to equation 7, where I've just combined these fractions and taken the reciprocal. That is, R equivalent is also equal to R1 times R2 over R1 plus R2. So this is an alternate representation for two resistors in parallel with their equivalent resistances. Remember, there's different equivalent resistances for any particular configuration of resistors. This is so unique to this particular problem. Now what we're doing is really just changing the labels. Bottom two resistors in our problem actually are R2, the original resistor, and now a new resistor, R sub L, or the load resistor, that's added in parallel across it. And so there's some there's some current through I2 and some current through the load. Both of those have to add up to I, the current through R1, just up above it, and through the entire circuit. So just replaced on the previous slide equation 6 with equation 8, where R1 has become R2 and R2 has become RL, and then same for equation 9. This tells us how we can write this more complex situation as a single component. So now we do the same substitutions with the original voltage divider equation. Repeated here is equation 10. That becomes then equation 11. R2 becomes our equivalent. R1 as here, and R2 becomes our equivalent. That's R1 is the same in both circuits, just R2 has been replaced with this new combination resistor made out of the two in parallel. Okay, so at this point, we just have to really substitute in our expression for our equivalent from the previous page, and then do a whole bunch of algebra. So you see everywhere I have our equivalent, here written equation 11, I have taken and replaced it with the full expression for our equivalent, which was R2RL over R2 plus RL. So that's where the top went. And then this lower R equivalent in equation 11 got replaced by this entire expression here. And it's a matter of simplifying mathematics. Briefly, I'm going to multiply the second set of parentheses, both top and bottom, by the quantity R2 plus RL, which leaves me with this modification. And then the R2 plus RLs actually cancel with the term in parentheses otherwise. And after some further simplification, I can rewrite my expression for the loaded voltage, that is the voltage with the load attached, as this equation 14. So again, anytime you see a new equation, you have to ask yourself, does it make sense? Does it make sense in terms of the units, first of all? The answer here is yes. We should have a voltage on the left-hand side, because we're calculating a loaded voltage, and a voltage on the right-hand side, which means this entire expression with these resistors should be unitless. And indeed it is. We have units of ohms on the top, and on the bottom, the expression in the parentheses here has units of ohms. It's an ohm squared over an ohm, which is an ohm, plus ohms, which is still ohms. So ohms over ohms is unitless, voltage in, and voltage loaded. Next, we have to consider some limiting cases. Of course, if the input voltage is 0, the loaded voltage is also 0. You can think of some other limiting cases, but the particularly interesting one here is that it reduces to the original unloaded voltage divider equation. If the output isn't open, right? So output is open, the same as we're back at the unloaded case. That is, we're not adding any resistor at all. That is, the loaded resistor load essentially has an infinite value. And 1 over an infinite value, RL becomes very, very large compared to R1 and R2. This entire expression in parentheses becomes 0. If this expression were to go away, you would see equation 14 would look exactly like our original equation 10 for the voltage divider. So this is a case in which the math makes perfect physical sense. If I take the limiting case that brings me back to my original situation, I recover my original situation. This also can be used to give an estimate of the significance of the loading effect. Let's see how that works out with some numbers. So you're just putting those resistor values from before. Remember the top resistor was 11K, where most of the voltage drop happens. The bottom resistor, R2, is 1K. So just substituting in the numbers, I always keep my numbers, my units with the number as I do calculations. I find that my loaded voltage is no longer 12 volts as original, but instead is 0.991 volts. So it's dropped from 1 volt to 0.991 volts over here by going through the addition basically of this extra term in the denominator, equation 14. All right, what does this mean? So here's what our answer looks like. Same configuration of resistors, but having added this 100 kilo ohm, although most of the current continues to take the path of least resistance through the 1 kilo ohm resistor, a small fraction of it goes through the load, resulting in a different voltage drop. And so our loaded voltage is 0.99 times the original output voltage, or 0.99 volts, since our output voltage was originally set to 1 volt. Or in other words, loading our circuit with a 100 kilo ohm load drops the output voltage by nearly 1% in this particular example. And it would be a different answer if we had different resistors in the original voltage divider. Now, using a smaller resistor for the load is actually worse. So if you were to redo the mathematics and replace this 100 kilo ohm load with, say, a 10 kilo ohm resistor, you would find that the output drops even more, about 10%. Now, luckily, we don't have to worry about too much in modular analog synthesizers, as typically we always at least have a input voltage of 100 kilo ohms, or typically quite a bit more, or we use one of the methods we'll talk about in the next lecture for solving this problem. But smaller resistors are definitely worse, dropping that voltage even more. In particular, you could say, well, what's 1%? I could tweak it back up with a potentiometer or something like that. But this is actually a significant issue because if you're using this 1 volt to provide a control voltage that, say, you were going to tune to middle A, pitch of 440 hertz, that 1% voltage difference from plugging into the VCO would have a pitch shift of actually about a couple of hertz, which is something the human ear can definitely hear, especially if you're trying to tune it. You'd hear some beat frequencies, and you basically would be already out of tune before you even started optimizing the rest of the circuit. So again, this comes from some of the current being diverted to your load, and seemingly there's no way to avoid that, and there certainly is no way to avoid that if you limit yourselves to just DC circuits with resistors.